The exams are up here on this table if you haven't picked up your exam. And a little quieter in here today, smaller group. The results of the exam, I believe the average, I don't know, did I send the average out? Yeah. Okay, so, but there were some really low grades in there that kind of brought the average down. There was a 0 in there, and there was like a 30 and something like that. So it's kind of skewed. I did send out an email to specific students only that basically I was concerned about. So if you got an email that said, hey, you're getting this email because I'm concerned about your progress in the course, blah, 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 then I would hope that you would come talk to me and not just sit there and continue to be where you're at. The next big deadline for us is the 12th of November is the last 13th? I don't remember. It's 13th to last day to drop? Friday the 13th. Okay, so, but the thing is, we're not going to have another test before then. So there's really not a whole lot, there's not going to be another major grade that's going to let you know where you are. So you have to make that determination before, you know, whether or not you want to stick it out or not. Anybody who does decide that they want to drop the class, you're welcome to continue to keep coming to class. In fact, if it's your first exposure to Cal 1, I would encourage you to continue to come so that the material is not, you know, when you do retake it, it's not like brand new. All right? Okay, so we move on. We're going to start Chapter 4 today. Chapter 4 is applications. Of the derivative. Now there are a tremendous number of applications when it comes to the derivative. A lot of different things that it can be used for. We've seen it's used for like instantaneous rates of change. We've looked at problems where you can relate rates to each other, the word problems that you didn't really care for, but you saw how powerful the technique of differentiation was. These applications here we're going to look at, I think there's really two main categories, well really three, but let's just look at the first two right now. Two main points that we want to take away in the next maybe 3 days of meeting together, and that is this. First, if somebody gives you a function, so if you're looking at a function, and let's say that function is defined on a closed interval. So f is given to you on capital I, which is going to stand for an interval where I is closed. Closed means it includes both the endpoints and everything in between. So in this case, it would be the interval AB. Do you see it in the picture? Closed interval from A to B. So your function is defined at A, at every point in between, and at B it's defined. If you ever have a function given to you on a closed interval, and that function is continuous. Now what does it mean to be continuous?
You don't have to pick up your pencil.
Yeah, basically that you don't have to pick up your pencil when you draw it. It's nice and smooth and connected together with no jumps, right? If it's a continuous function, then would you agree that it should have like a highest value and a lowest value? It should have some point that is higher than every other point on the graph, and it should have some point that's lower than any other point on the graph. In this particular case, it looks like maybe this would be the highest point, and this over here would be your lowest point, right? And the question for us is, can we figure out where these happen? Can we actually determine where the function is the highest and where it is the lowest, right? Now, in contrast to this, the other major theme of this chapter is going to be, what if the function was not on a closed interval? In other words, what if the function just continued in both directions forever? Then you would have something like this, where you've got this function. I'll just draw it like this. It could do so many different things. That's the way I'm going to draw it. The arrows at the ends just represent that the function continues with that pattern. This would mean it's just going down here forever, and then over here it's going to go down forever, right? Does this function appear to have a highest and lowest point? It does look like it has a highest point, right? Looks like maybe right around here we have a highest point. But lowest, no, it doesn't look like it, because this continues down forever, and so you're not ever going to have a lowest value to the function. So the question would be, can we find this point? Can we figure out where this is occurring? Well, these are going to negative infinity, but could we figure out the x value that turns out to give us that highest value, right? That's the main thing. So those are the two main themes. Somebody gives you a function. If it's on a closed interval, can we find the highest and lowest points if it's a nice, smooth function? Or someone gives you a function, and did that just get hit? So it's all right if it did. I just got to fix it before. Let me move this up a little bit. Whoa. Let's see here. Bring it this way. Okay, what was I saying? If we have a function on a closed interval, looks like we can find a highest and lowest point. If it's on an open interval, which would mean the interval would change to being open, is there a way to do it? Can we find a maximum and maybe a minimum value, a highest and lowest point? So that leads to two different methods. There are two different approaches depending on what you have. There's what's called the closed interval method, which is what we're going to start with. Then after the closed interval method, we learn the basic, they don't really call it the open interval method, but I will call it something like that. It's just not the closed interval method, all right? So before we can proceed, we have to get some definitions in place, some language, so that when I'm saying these things, you understand what I'm talking about. We're all on the same page, all right? So the notes that are online talk about all these different definitions. First of all, the first definition is what's called the absolute maximum or minimum value. So right now they're not telling you you have a closed interval, right? It's just saying you have a function defined on capital D. So you got some function defined on capital D. And the capital D here, it stands for the domain. The domain might be an interval that's closed or open. Here it's just D. If I draw something like this, an absolute maximum is the height of the function at some point that is higher than any other point on the graph. We call that the absolute maximum. So this right here, let's say we call this number C, then f of C, that height is the absolute maximum. Highest point on the graph, right? That's also called, other language, the global maximum. So absolute maximum and global maximum are the same thing. That's in the notes also. I just say it down here. On the other hand, if we have a point that is the lowest point on the graph, see, I should have flipped this over. That would have been the highest point, right? Sorry, I didn't notice that I had put that arrow up. That wouldn't have been an absolute maximum. Okay, this particular graph would have an absolute maximum, but would it have an absolute minimum? No, it would not. So if you flip the graph over, right, and made the arrows go up, then you would have an absolute minimum, wouldn't you? Okay. Everyone understand the idea? Is it possible to have a graph that has both an absolute maximum and an absolute minimum if I never close off the ends? Like I make the ends go forever doing something. Yeah, I should be able to draw something like that. How about this? I'm sure I could come up with a function that behaves like this. Maybe it goes... So as you go out to infinity or negative infinity, right, the function tapers off to 0. But here and here, those 2 points, you would have an absolute minimum here, right? And you would have an absolute maximum here. Yes? Yep. All right. So it is possible, even though my function is defined everywhere, to still have an absolute max and min. But you're not guaranteed one all the time. It could happen, it could not. How about a function like x cubed? Or any cubic function for that matter. Does that have an absolute maximum? No. Does it have an absolute minimum? No. So there's no lowest point on the entire graph. There's no highest point. So it's never guaranteed when your interval is opened up like this. It's never guaranteed that you have to have it. All right. So, but we do have some things called local maximums and local minimums. And when it comes to local maximums and minimums, you do not have to look at the entire graph. You look at just a small region of the graph, and you look for a highest and lowest point. So let's go to this x cubed, or this cubic function here. This point right here is not an absolute maximum, but we would call it a local maximum. Because locally, it's the highest point on the curve, right? And this is where we get into some kind of ambiguous wording. When we say near this point, what do we mean by near? Around. Right, around. But how close is close, right? Like when we say things are close, it's hard in mathematics to really nail that down. We do it precisely in more rigorous math classes using delta epsilon proofs and things like that. But in here, when we say near, it's just more of a visual thing. Do you all agree that's the highest point in that region, that neighborhood? King of the mountain on that mountain, that's it, right? And then you have here a local minimum. Nope. How about these 2 points here? This was an absolute max, right? Or global max. This was an absolute minimum or a global minimum. What about local? Yes. It's also a local max and a local min, isn't it? I mean, locally, it satisfies the definition. It just has to be the highest point in that little region. Well, it is. In fact, it's the highest point in the whole thing. So this would also qualify as a local max, and that would qualify as a local minimum. All right? Also keep in mind that the absolute max, the absolute minimum, global max, global min, local max, local min, that's the y value of the function. Right? So when if I tell you, hey, the absolute maximum value of this function is 20, I'm saying the maximum height it is 20. I could also say where it happens. So like let's say that this was 20 high here, and let's say that this happened at 5. The absolute maximum of this function would be 20. It happens when x is 5. So just some clarification on that you're always referring to the y value when we talk about maximums and minimums. All right, that's just visualization stuff, which I won't go through. Okay, and then we get what's called the extreme value theorem, which I will write down on the board because it's important enough to write down. All right, the extreme value theorem says, this is 4.1.7 in the notes, if f is continuous, right, on a closed interval AB, then f attains both an absolute maximum and an absolute minimum on that interval. So somewhere in that interval, it's got to have a highest point, and somewhere it's got to have a lowest point. Has to.
If it's a constant, you still have?
I was hoping you would bring that up. Yes. We'll talk about that. Give me a second. All right, so if the function is continuous, then the function has to obtain both an absolute maximum and an absolute minimum on the interval. And I think you can convince yourself of this by just trying to make it not happen. Okay, so let's say I have some point A and some point B, because my function is defined on the entire thing. Try and connect those two together with a nice, smooth, continuous function and not have a highest and lowest point. I mean, there's just no way to do it. So like if you try and be clever and do a straight line, then the endpoints, right? This endpoint would be your highest and that endpoint would be your lowest. If you do any wiggling around in the middle, you could do something like that, and then it would still be the endpoints, right? Or if you go up a little bit higher like this, then your absolute maximum would be up here, and your absolute minimum would be that left endpoint still, right? And no matter how you do it, no matter how you try and connect these together with a nice, smooth, continuous curve, you're going to have to get a highest and lowest point, unless perhaps you draw a constant function. So let's look at that. Everyone okay with this? Okay, so let me try and draw a constant function. That would mean I start here, I end here, and I just go straight across. Is there a highest point? Well, you have to go back to the definition, okay? So look at the definition. Remember inequalities. A being greater than B means that A cannot be equal to B, right? A has to be bigger. If I write A greater than or equal to B, that means that they can be the same. And when you go back to the definition of an absolute maximum, notice that in the definition, when we define absolute maximum, we use the inequality with a greater than or equal to symbol. Meaning that when you say that you have a maximum, absolute maximum value, it is the biggest or equal to everything else in the function. Where here, if I pick this point right here, is that point right there, is the y value of this point bigger than or equal to every other point on the graph? Yes. But it's also less than or equal to every other point on that graph, isn't it? So let's say that this had a value up here, I don't know, I'll just make up a number. How about d? What would the absolute maximum value be? D. But what's the maximum minimum value, or the absolute minimum value? D also. So your absolute maximum and the absolute minimum are the same. But that's only for a constant function. Would that happen? If you got any wiggling around, then you're going to have something else. Understand? All right, local max. Let me see here. We got our extreme value theorem. All right, then we get to what's called Fermats Theorem. And this is, if anyone knows anything about Fermat, this is not Fermat's last theorem, okay? This is just one of, Fermat's last theorem is a very famous theorem. This is another one. All right, says if f has a local maximum or minimum at a point C, and the derivative of the function at C exists, then the conclusion is the following. But let me try and let's see if we can determine the conclusion of this theorem without actually cheating and looking at what it is. So Fermat's saying this. Fermat's a mathematician, okay? It's long gone now, right? Let's say we have a local maximum or local minimum, which means you're the highest, the king of the mountain, right? Or the bottom of the valley, whatever. Let's just do king of a mountain example. So who cares what else is happening on the function? Let's say just right here, you have a highest point. Fermat says, if you have a local maximum and the derivative exists. So remember, the derivative is a limit, isn't it? You go back to the very first definition of the derivative. It was limit h goes to 0, f of x plus h minus f of x all over h. We've seen that limits can exist and they cannot exist. So if you've got a highest point or a lowest point in a certain neighborhood and the derivative actually exists, means it gives you a number, then what must that derivative be? 0. Because that means the slope of the tangent line, right, which is what the derivative is, the slope of the tangent line would have to be 0 if this is going to happen. This tangent line right here, right, f prime of c, c was where it happened, right? You have a local maximum or minimum at the point c, then the derivative at that point must be 0. Does it make sense to you that this would be true? Yeah, that's what the theorem states. Now we have to be extremely careful with this theorem, all right? Because it can be abused, it can be used improperly. Let me show you something. Does this theorem say this? This is a question to you. Do you think this is true? If the derivative is 0, then if the derivative at some point is 0, then f has a max or min at c. Do you think this is true? True or false? I have one false. True? False? So I'll offer someone bonus if you think this is false to draw me a counterexample. To just come up here and sketch out a function that has a derivative of 0, but you don't have a maximum or minimum there. You want to try it? Go ahead.
That's pretty bad, right?
Well, I think we understand what you're doing. Oh yeah, you're on camera too. I guess I should have told you you'd have to be on camera.
So how about...
Okay, so what point is it that you want us to look at?
this point right here?
All right. We'll take it to the class and we'll ask them. Thank you. What do y'all think? Is this an example where if we look at the function at c, which you're saying is 0, that the slope of the tangent line, right, the derivative is 0, but we don't have a maximum or minimum there? Do y'all buy that?
Yeah.
Let's look at this is actually, we could use this as this function. I don't know if that's the one you want to use. There's a bunch you could use, but let's just say x cubed. Doesn't x cubed kind of look like this? What is the derivative of x cubed? 3x squared. What is the derivative of this function at 0? 0. So the slope of the tangent line here is 0, isn't it? But it's not a maximum, it's not a minimum.
If it's local, wouldn't it be a max and a min?
What's that?
If it's a local, wouldn't it be a local max or min right there?
This would be neither. Because if you, let's zoom in on that, okay? It's happening like right around, well, that's not a very good drawing. It should flatten out a little more. But you cannot say that that's the highest point on the graph because if you just go to the right of it, there's a point higher. You can't say it's the lowest because if you just go to a point to the left of it, there's a point lower. So it doesn't have that valley-looking thing. Do you all see that? So that's why theorems are very important the way they're written. What Fermat says is if you have a local maximum or minimum and the derivative exists, it must be 0. Not the other way around. This is a logic thing, okay? And this is important, especially for your computer science and math majors and things like that. Logic, order of things. If you are a Texas citizen, C-I-T-I, Z, right? E, citizen, then you are a U.S. citizen, right? Is that true? Right. Agreed? Does it work the other way around? If you're a U.S. citizen, are you there a Texas citizen? No. Right? Was that a hand? No? Were you raising your hand? No? Okay. So it doesn't work the other way around. That's the way theorems are too in mathematics. When they're written a certain way, you always have to go in that direction. What's the only time you can go both directions? I think I might have. If and only if, right? If it was written, you know, U.S. Texas citizen, if and only if U.S. citizen, that would mean you can go both directions. But it wouldn't work for this, would it? Okay, so, all right. So be very careful with this, all right? With this theorem, it can be abused. All right, so now we have another definition. Well, you know what? There's one more thing in Fermat's theorem that we can address now. It might be a little bit too early, but Fermat's theorem said that if you have a local max or min and the derivative exists, right? And the derivative exists, then the derivative must be 0. Can somebody, another bonus opportunity here, Ryan's already got one here. Can somebody here draw me an example, or draw us an example of a function that has a local max or min, that does have one, but the derivative is not 0? And go for it. Go ahead. You're going to be on camera, though. Is that okay? All right. Yeah. Now, hold on. Before you draw it, let's let everyone think about it. Try and think of a function that it has a local max or min, but the derivative does not exist at that point. So see if you can think about what that might look like. Let's wait like 10 seconds. Let's wait 10 seconds. You can draw your x, y axes. Anybody think they might have something? Okay, let's see. Let's see if yours looks like this one. Let's see. Okay, so where?
Like, there's the min and there's the max. They still have like, it's just you're looking locally, so the line would still be straight.
You're closing your interval. Mm-hmm. If this is on a closed interval, does everyone agree that this would be okay? Yes? I agree with that. Good. Someone have something else? You want to draw something else? This will work only if we close them off, right? Okay. Go ahead. You're going to be on camera. Is that all right? All right.
Want me to erase that or leave it?
No, leave it up.
I'll do it underneath.
There you go. Okay. Very good. So you're saying at these points, right?
Points, yes.
At these corners. That's good. Remember we said derivatives could not exist at corners, right? So this is a local maximum. It is, because this is a continuous function I can draw without picking up my pencil. But at that point, we have a corner, and you can't find the derivative there. So that, yeah? You could also do a cusp, which is pretty much the corner. The same thing, but just the shape is a little different. It goes like this. So all of these are examples of functions that you do have a local max or a local min, right? And the derivative, but the derivative there does not exist, except for this one, but that's the closed interval, so that's a little bit different. These two, local max, local min, local max, derivative doesn't exist there. All right? All right, let's continue. Definition, critical number. And again, this one is so important that I will write it down up here. It seems to me, I don't know if by looking at this, that if we're going to have local maximums and minimums, the derivative is either going to be 0 there or it's going to not exist at all. We're either going to have a corner or we're going to have a nice smooth curve where the top of the graph is. So that's what, since those 2 points or those 2 types of situations are so important to us to be able to determine maximums and minimums, we have a special name for them. They're called critical numbers. The critical numbers of a function are any numbers, any number, or possibly numbers, you could have more than one, any number of numbers C in the domain of the function. Okay, so in capital D, which is the domain of the function, such that one of these is true. F prime of C equals 0, or F prime of C is undefined, does not exist. So let's look at an example, okay? I'm gonna give you an example real quick. We're going to take a look and see if we can determine what the critical numbers of this function are. Just going to pull something out of the exercises. Okay, so how about we'll go pretty easy to start, I guess. F of x is x cubed plus 6x squared minus 15x. I would like to find the critical numbers. So the critical numbers are anywhere where the derivative of this is 0, or anywhere where the derivative of this does not exist, right? So let's first just take the derivative. What's the derivative of this function? 3x squared plus 12x minus 15. Agreed? The critical numbers are going to be anywhere where that's 0 or anywhere where that doesn't exist. So let me first figure out where it's 0. Where's the derivative 0? Question. Well, that's wherever 3x squared plus 12x minus 15 is equal to 0, right? And that's a quadratic equation. So you need to be able to factor it or do something to it, right? Everyone needs to be able to solve a quadratic equation in this class. I think the easiest way is maybe factor out a 3. Does that help? Does that help you factor this? This is x plus 5, x minus 1, right? And so You set these factors equal to 0. You can chunk the 3, right? 3 can never be 0. Just divide both sides by 3, it's gone. So what are our two critical numbers from here? -5 and +1, right? These are two of our critical numbers. These are the values that if you plug them into the derivative, you get 0, right? Now, the other thing we have to look at is anywhere where the derivative doesn't exist. So when I look at where does the derivative not exist? dne does not exist. Where does the derivative not exist? Well, your derivative is a polynomial function, isn't it? And it's defined everywhere, isn't it? There's no division by 0. There's no square roots. There's no craziness in a polynomial, right? So this is never going to happen. Your derivative is always going to be well behaved. So I can scrap this because f prime is a polynomial. The derivative is a polynomial. Yes?
So like, I guess where it wouldn't exist if we had a rational function?
Yeah, if you have rational functions, but then even then you have to be a little careful because to be a critical number you have to be in the domain of the original function. So I'll show you where you have to be a little bit careful with that.
Can you have more than one min and max?
Local, yes. Locally, yes, but not absolutely.
What if it's like a sine function?
You would still have the same absolute maximum, but where it happens would happen at infinitely many different places. It would still be 1 and -1 for max and min. What I'm going to do right now is I'm going to graph this function. It was x cubed plus 6x squared minus 15x. And man, it's hard to see that. Geez. Okay, so what I'll do is I'm going to change my bounds a little bit here. X is going to go from -10 to 10. Oh, wait, you know what? I don't want that either. My view, -10. See if this is enough. There we go. You all see this? This is the cubic function, all right? Where is this maximum and minimum occurring? Let's see. It looks like somewhere around here we go up and we get a max right there, local max. And then here we get a local minimum somewhere in here. And that looks like, I mean, is it potentially, could it be -5? Yeah, it looks like it from the graph. And then doesn't it look like the min is happening at 1? And it's going to turn out that's the case, but I want you to see that what we're doing here is we're saying, look, this is a potential list of where interesting things are happening on the graph in terms of local max and min. I'm not in any way saying that I'm guaranteed to have a max or min here at all, right? It's not guaranteed. It's just saying we know that if it does happen, if we do get a max and min, if it does happen, then we know that if the derivative exists, that it's going to happen at one of these. If the derivative doesn't exist, well, we haven't really looked at that yet. Okay, is that all right? Understand? Now, I'm going to show you something else. And I feel like I've shown you this already, so I'm might be already walking over the same path here, but did we talk about this yet? Just stop me if I have. Where if you look at back in college algebra, when you have parabolas, ax squared plus bx plus c, there's a very important point on it called the vertex. It's the highest point on the parabola. If the parabola is drawn where it opens up, it would be the lowest point on the parabola. Yeah? And do y'all remember seeing a formula for that? And the formula was, we call this point HK, right? H was the x coordinate, right? Do y'all remember this? H is -b over 2a. Do you remember seeing that formula somewhere when they were there? Yeah?
is with that, the value is that.
K is that plugged in, right? So check this out. We know for a parabola that it has a local minimum, right? Or a local maximum. That's it. That's the only thing that could happen, right? Local max, or absolute max really, but local max, local min, yes? Do we also agree that at the local max or local min, you would have a derivative that would be 0? Yes? So the derivative would exist and it would be 0? Yes? So all I'd have to do if I want to know where this happens, and forget this formula is here, right? If I want to know where this happens, and specifically if I want to know the x value where it happens, I would just need to figure out where the derivative of that is 0, right? So take the derivative. Remember a, b, and c are constants. What's the derivative of that function? Well, the 2 comes out times a, so 2ax, agreed? Plus derivative of bx is b, plus the derivative of c, which is 0, right? And then take that derivative and, like in the critical numbers, set it equal to 0. Where's the derivative 0? Well, take 2ax plus b and set it to 0 and solve for x. So subtract b, you get 2ax equals negative b, and then to get x, you divide both sides by 2a. So you get negative b over 2a, right? So what we're saying is that whether or not it's a maximum or a minimum, doesn't matter, on a parabola, the x-coordinate of that maximum or minimum is going to have to look like this, negative b over 2a. And that's it. That's where it comes from. So it's just a result of what we're talking about now. Could you do something for a cubic? Like, imagine someone gave you like an arbitrary cubic function. Could you come up with the formula that would tell you where its maximums and minimums occur? You take its derivative and set it equal to 0, right? And if you take the derivative of this, you're going to get a quadratic equation, aren't you? And you can solve a quadratic equation. So you could actually come up with a general solution for where a cubic function would have maximums and minimums. What if this was a 4th degree polynomial? Well, then your derivative's a 3rd degree polynomial, and you have to set that to 0, and that's much harder. 4th degree, right? Or 5th degree, take derivative, be 4th degree. So we know that we know it's easy to solve linear equations. For quadratics, we have the quadratic formula, right? For cubic, do we have a formula? Is there a cubic formula, like the quadratic equation? Is there a cubic equation? What do you think? Probably? There is. There is. It's ugly. It's about a page, like half a page long. Yeah, it's not pretty. What about a 4th degree? What do you think? A 4th degree? You think there's an equation? There is. It's very long. It's, I think, like a page and a half, 2 pages long. It's ugly. 5th degree, what do you think? No. No, it's not. It's actually proven that there is no formula. So listen to what I'm saying. I'm not saying nobody has found the formula. It's been proven the formula doesn't exist. That you cannot ever come up with a formula for it. So the 4th degree is the highest we go. If you have polynomial 4th degree equal to 0, we have a formula for it. After that, no formula exists. So solving equations that are 4th degree and higher involves some other method. And the method that most computers use is what's called some variation of what's called Newton's method. And that is something that uses the derivative. It's one of the applications of derivatives. So most of the time, when a computer is trying to solve an equation, it is using calculus to do it. It's written into the program. All right, I'm getting off topic, sorry. All right, let's do something that's a little more interesting than that. That was a polynomial, it's kind of boring. Let's do the critical numbers of this. So, example, find critical numbers of g of x equals x to the 1/3 minus x to the negative 2/3. That's more like it. Now this thing has always had problems graphing things like that. Let me see what it does. X to the 1/3 minus x to the negative 2/3. I need to get my window back closed here to set the corners. Ooh. I just want to get an idea of what this thing looks like. That's all this computer graphed so far. It doesn't look like we have any places where the derivative is 0, do we? Does it look like it to you? Where the derivative is 0? Okay, let's go through the method. Let's find the critical numbers. So we're going to need the derivative, right? The derivative of this, 1/3 comes out, right? Subtract 1 from 1/3, so 1/3 x to the negative 2/3. Minus or plus? Plus 2/3 x to the negative 5/3, right? Subtracting 3/3 from negative 2/3 is negative 5/3. Oh, okay. And you know, prior to this, it was like, okay, there's a derivative. That's all we had to do. But now we have to set this to 0, right? Which I said at some point we're going to have to work with this algebraically. And today's the day. So I want to know, first of all, where's that derivative equal to 0, right? That's the question. So I have to set that equal to 0. So I'm going to write this a different way. 1 over 3x to the 2/3 plus 2 over 3x to the 5/3 equals 0. Do you all agree that's the derivative? I just kind of dropped my exponents down. Do what?
Can you like say equals 0 and take out that 1/3 x?
Yeah, you could pull a 1/3 out right now. Yeah, you could. Yeah, there's a lot of things we could do, right? I mean, that's one of them. As long as you don't break any algebraic rules, we should all get to the same solution, right? How you do it is up to you. I'll just show you how I'm going to do it, and then if you have a different way, then that's okay, as long as we get to the same thing. I'm going to combine these into a single fraction, so I'm going to get a common denominator. That's what I'm going to do. Put these two together. So what would the common denominator be? 3x to the 5/3. Common denominator would be 3x to the 5/3. So how can I make this one an x to the 5/3? What do I have to multiply it by? X to the 3/3, right? X to the 3/3, which is x to the 1. But I'll write it as x to the 3/3 just so everyone understands what's going on here. See, when we multiply this x to the 3/3 times x to 2/3, you add the exponents, and you would get 2/3 and 3/3 is 5/3, wouldn't you? But really, technically, I'm just multiplying by x, yes? It's just x. So this becomes x on top over the common denominator, right? Plus 2 on top, and then what? Common denominator? 5/3. Equals 0. Understand? Now, when a fraction equals 0, the only time or the only way that can happen is what? If the only way that a ratio can ever be 0 is if the top is 0. Okay, so keep this in mind. This is something I remember in Cal 1 when I first learned it. I was like, okay, I'm going to need that like the rest of the way. Look, if someone ever gives you a ratio, A over B, and they tell you that that ratio has to be 0, could you not always multiply both sides by B? Yes? And cancel these B's out, and 0 times B should always be 0, right? And that just results in A must be 0. Right? Could B be 0? No, because then it wouldn't even be defined, right? So you don't even have to worry about B ever being 0 to try and figure out where the whole thing is equal to 0. So when you're at this point, what I'm going to do is say x plus 2 equals 0. All right? And then from there, I'm going to solve it and get x is negative 2. That is a critical number of this function. So long as that number is in the domain of the function, all right, which we didn't look at the domain, but I'm going to go back and look at the domain in a second. Are we done with critical numbers? No, because there were two things I have to look for, right? The second thing I have to look at is where does the derivative not exist? Well, yeah, let's look at the derivative again. The derivative, oh wait, it wasn't f, sorry. This was g, pardon me. It was g, right? G. G prime doesn't exist. The derivative, we had a complicated version of the derivative. It was like 1/3 x to the negative 2/3 plus 2/3 x to the negative 5/3, right? But we cleaned up that side, and it all turned into this, didn't it? Okay, so this is really a cleaned up version of the derivative. And so if I'm saying, when does this derivative not exist, then I need to look for anything that's going to screw this derivative up. Which would be what? If the denominator is 0, which would be x is 0, right? If x is 0, there's a problem here. So if x is 0, this derivative does not exist. Now, remember also that this means the cube root of x to the 5th, right? I don't have any domain issues there, right? I can take cube roots of negative numbers. But if that had been square root, we would have to throw out all the negatives too, right? We'd have to worry about that? Okay, just want to make sure we're thinking that way. It appears that those are the only two critical numbers. So does that mean that I have to have a maximum or minimum there? No, it's just saying that something interesting is happening there with my function. Let's see if these both belong to our group of critical numbers. These have to be part of the domain of the original function, right? So maybe I should have looked at the domain first. Let's go back. G of x was x to the 1/3 minus x to the negative 2/3, right? Which is really cube root of x minus 1 over the cube root of x squared. Isn't that what that is? Were there any domain restrictions on our original function? Anything I cannot plug in here got to be a void? X couldn't be 0, right? If x is 0, don't you get division by 0 here? So when I look at this, the domain of G, x cannot be 0 is my domain restriction. Which means, can this be a critical number? What's the definition of a critical number? A critical number of a function f is a number c in the domain of f such that one of those two things is true. So in order for this to be a critical number in my list of critical numbers, it has to be allowed to be in the original domain of the function, which it's not. So this is not a critical number. Understand? I only have one critical number here, and it's the number negative 2. Okay? Something interesting is happening at negative 2. But my graph is not, it's not doing a good job here. It doesn't draw anything to this side. That's a limitation of that program. I wonder what Mathematica will do with it. Do y'all want to see a graph? Okay, let me see. I might have a problem with Mathematica too. Let me see, plot. Probably not. Yeah, it's not doing that either. No. I'll try one more thing. It was cube root of x, right? And then minus 1 over the cube root of x, but then that quantity squared. Let's see what it does with this. Ah, there we go. Okay. I had to try and be smarter than it. It's hard to tell from this, but at x is -2, it is quite possible that that's a local maximum. That if you go to the right, it starts dropping down. If you go to the left, it starts dropping down. Locally, that could be a maximum. In fact, it looks like it is. I can tell you real quickly. Do you want to know? We're going to do this later, but do you want to see what a quick check would be? Just so you can start thinking about it? Think about this for a second. We know that right here, the slope of tangent line is flat. If this is a maximum, it looks like that, right? Kind of, but zoomed in. It means to the left it goes below, right? To the right it goes below. Do you agree then that to this side, I should be increasing, and on that side, the function should be decreasing, right? That means the derivative over here must be positive. Remember, slope of tangent line being positive means you go up. Over here, the derivative must be negative. That would mean slope of tangent line would be going down. Do you understand the basic idea here? If your function goes up and then goes down, then that would look like a local maximum, yes? So what I'm going to do here to convince us is I'm going to look at my derivative. Here it is. And I'm going to plug in a point, if this is my number line, -2. Just going to pick a point somewhere to the left of -2, like -3. And if I plug that -3 into here, let's see what happens. So what's g prime of -3? We get -1 on top. Tell me about this. The cube root of a negative number would be negative. To the 5th power, still negative. Times 3, still negative. So the bottom is a negative number. So the ratio of a negative divided by a negative would be positive. So I know that to the left of -2, my derivatives are positive, which means my function is going up. When it gets to -2, what happens? It's 0, which means it's flattened out. And now I'm going to check to the right of -2, which would be something like -1. If I plug -1 in here, what do I get? Positive on top, and on the bottom, it's still going to be negative, right? So you're going to get a positive on top, and you're going to get a negative on the bottom, and that would be a negative number, and that means it's going down. So in fact, at -2, it is a local maximum. But we'll do more of that later. Just trying to convince you that we did find something that when you look at it graphically, I'm not sure anyone would look at that graph and be like, oh yeah, at -2, that looks like a local maximum, right?